So if you're ready, we can start. Okay.
Yes.
Welcome everybody to this pre-seminar. This is the first online version. So our speaker is Andrea Sciandra from the University of Turin, and he's going to give us a brief introduction to Níchols algebras. Please.
Okay, so first I thank the organizers for this opportunity. I would like to start with some references. So Níchols algebras appear for the first time in a work of Níchols to construct new example of algebras. So in particular here, the small quantum group UQSL3 appeared. Independently, they appeared in the famous paper of 1999 of Voronovich as the invariant part of his non-commutative differential calculus. Later, in a paper of 1993, Lustig also described the positive part of the quantum universal enveloping algebra by a universal property which is equivalent to that of Níchols algebra. Finally, I would like to mention the famous lifting method introduced by Andruszkiewicz and Schneider in 1998 that showed that the classification of Níchols algebra is really an essential step to classify pointed of algebras. And we will also speak about this at the end of this talk. Okay, so I would like to recall the explicit construction of Níchols algebra starting from the very beginning, so starting from the definition of algebra and braided algebra. So everybody knows that bialgebra is just a datum of an algebra, BMU, and the coalgebra, B delta epsilon, such that delta and epsilon are algebra maps, or equivalently, M and U are coalgebra maps, and this means that the following conditions holds, where we use the Zwittler notation for the delta. And a bialgebra is an off-algebra if it is equipped with an antipode, so a linear map from B to B, which satisfies the two equations here. Okay, now the classical example of off-algebra is the group algebra over a field with coproduct, counit, and antipode defined on every element of G in this way. Delta of G is G tensor G, and epsilon of G is the unit of the field, so G is group-like. And the antipode over G is the inverse of G. Now, the category of algebras is the category of monoids inside vector spaces, but one can build the category of monoids inside any braided monoidal category, and with braiding sigma. And the big difference between a standard of algebra or of monoids in M is just the compatibility between delta and M. So the one displayed here that tells you that delta is multiplicative. And you can see that here you have the braiding of your category. And if you consider vector spaces, you have the flip map and you recover the classical multiplication of multiplicativity of delta. Okay, so in the following, we will consider H of algebra with bijective antipode. And I just recall the definition of Jeter-Drinfeld modules. Of a Jeter-Drinfeld module over H is just a vector space with the left H module structure and the left H comodule structure, which denote in this way, omitting the sum. And these two structures are compatible in the following sense. So we have an equations for the coaction over the action. Okay, now the category of Jeter-Drinfeld modules is braiding with this braiding here. So you can see that for every Jeter-Drinfeld module X and Y and every tensor are X tensor Y, what the braiding do is just to do coaction over X, then flip X0 with Y, and then do the action of Y over Y. Now, if you consider the group algebra, and then the Jeter-Drinfeld modules over groups are just graded vector spaces. This because the category of comodules over the group algebra is isomorphic to graded vector spaces, equipped with a KG action compatible with the grading. And morphisms are just K-linear maps that are also KG linear and preserved gradings. Now, this category is in fact braided, as we said before, and you can recover the braiding in this specific case just putting the correct coaction. In this case, when you choose an element V in a component Vg, then the coaction is just given by G tensor V. Okay.
This works for every group, right? So you don't need a finite group or something.
No, exactly.
Okay.
Exactly. You just have to put here the coaction, and the coaction is exactly the one that gives you for every V in Vg just its degree tensor itself. And but yes, for this holds for every group. You can consider Dieter-Drinfeld modules over a group algebra, arbitrary group algebra. Yes. Okay, and now what is an Hopf algebra in Dieter-Drinfeld module? So it is just a Dieter-Drinfeld module such that it is a monoid inside Dieter-Drinfeld module, so it is an algebra, and multiplication and unit are left H linear and left H collinear. It is a comonoid in Dieter-Drinfeld module, and this means that it is a standard coalgebra plus delta and epsilon are left H linear and left H collinear. And delta and epsilon satisfy the following condition, and you can see that these three are exactly the same for every Hopf algebra, while in this case, for the multiplicative of delta, we replace the flip map with the braiding of Dieter-Drinfeld modules. And okay, they are also equipped with an antipode. So in the specific case of group algebra, I don't want to give the details, but I've just graded vector spaces, which are monoid and comonoid inside the category of Dieter-Drinfeld modules over the group algebra. I just want to say that the fact that the multiplication and the unit are collinear just means these two conditions here, while the fact that delta and epsilon are collinear just means these other two here. Okay, now that we know what a braided Hopf algebra is, we can start with the construction of Níchols algebras. So consider an Hopf algebra H and the Dieter-Drinfeld modules over H. So take the base field in Dieter-Drinfeld module with the trivial action and coaction, and for every n bigger or equal than 1, V tensor to the n, so V tensor with itself n times, is still in Dieter-Drinfeld module, just considering diagonal action and diagonal coaction. Then also the tensor algebra, which is direct sum of all these V tensor, is still a Dieter-Drinfeld module with the direct sum structure. And it is also an algebra in Dieter-Drinfeld modules. Okay, and it holds the classical universal property that if you consider another object in monoids in Dieter-Drinfeld modules and a morphism F from B to A of Dieter-Drinfeld modules, then there is a unique morphism from the tensor algebra to A determined by this relation here. And you just use the universal property of the tensor algebra. So we know that there is a unique algebra map from TV to A, defined in this way here, and it is clearly also a morphism of Dieter-Drinfeld modules, so the unique in the category of monoids in Dieter-Drinfeld modules that satisfy this relation here. Okay, but it is something more. In fact, the tensor algebra is a graded connected Hopf algebra. So connected just means that the 0 degree is one-dimensional. Hopf algebra in Dieter-Drinfeld modules such that the elements of V are primitive elements. And what one does is just to define a small delta from V to A as iota tensor unit plus unit tensor iota, where iota is just the inclusion of V in the tensor algebra. And consider also the morphism 0 from V to K. Then using the previous proposition, we know that there are unique algebra morphism in Dieter-Drinfeld, delta and epsilon determined by this relation here. So delta composed with iota is the small delta, and epsilon composed with iota is 0. And with this delta and epsilon, the tensor algebra is a comonoid in Dieter-Drinfeld modules and also a bimonoid. But since it is graded by algebra in Dieter-Drinfeld modules, it is always an Hopf algebra in Dieter-Drinfeld modules, because you are able to build the antipode S in this way here. So it is an Hopf algebra in Dieter-Drinfeld modules, connected, graded and connected. Okay, and there is also this universal property that if you consider a bimonoid or opmonoid in Jeter-Drinfeld modules and the morphism from V to A of Jeter-Drinfeld modules, such that the image of F is in the primitive elements, then there is a unique morphism of bimonoids determined by the relation of before. And okay, we already know that there is a unique algebra morphism, so one just have to prove that this is also a coalgebra map, but then one can just consider this morphism here, delta A composed with F, small f, and since you are able to find two morphisms of algebras, which are these two here, such that composed with iota they are the same, then they must be the same by uniqueness of the universal property. And here we use that, in fact, that the image of F is contained in the primitive elements. So this is the universal property of the tensor algebra, and this result applies also when we consider a graded connected bialgebra and the morphism F from V to the first degree component, just because the first degree component is contained in the primitive elements, as we recall now in a minute. So the tensor algebra has this universal property. How can make from it this called Níchols algebra? So just give some definition and result for that holds for every graded of algebra. So when we have a graded coalgebra and we consider projection, then we can define this map for all n bigger or equal than 1. So start with the n component of C, do the delta n minus 1 times, and then the projection over the first degree component n times. Now, define this ICN as the kernel of this map. You can see that clearly the delta 1 is just the identity, so IC1 is 0, and then you just have the components with n bigger or equal than 2. And you can define the IC as the direct sum of all of these. Now, when our C is also connected, we know that for all n and for all x in the n component, the delta of x is just 1 tensor x plus x tensor 1 plus something which is in components of tensor of two components that have degree bigger or equal than 1, both.
Sorry, just a quick question. So in this definition of ICN, you wrote this is the kernel of delta 1n. What is this? Maybe delta I missed
1n are this map here.
Okay, it's written there. Sorry. Yeah. Okay, so
and what you do is just take the n component and do delta n minus 1 times. So you go in C tensor to the n, and then project
to the
n
C1
times.
part.
Yeah, exactly, to the C1 part. Then choose the kernel of this, and now if n is equals to 1, this map here is just the identity. So the kernel is 0, and then you can define IC as the direct sum of all the other components bigger or equal than 2, of degree bigger or equal than 2.
So just to understand this better, so what would happen, for example, for n equal 2? Can you say something?
Exactly, and then he's here, but I want just to,
Great.
to say.
Then I shut up, sorry.
Yeah, and so when C is connected, we know that the delta is of this form. So delta of x for every x in the n component is just 1 tensor x plus x tensor 1 plus something which is inside here. And you see that both of these two components have degree bigger or equal than 1. So in particular, the first degree component is containing primitive elements. Moreover, also from this fact also follows that when C is connected, the IC is a graded coideal. Okay, but then what happens, for instance, for C2? For C2, the delta of an element in C2 is of this form, is 1 tensor x plus x tensor 1 plus y tensor z, where y tensor z is an element here in C1 tensor C1. And you can see that when you project on C1 tensor C1, you obtain exactly this component here, so y tensor z. And so IC2 are exactly the element in C2 that are primitive. So such that delta of x is 1 tensor x plus x tensor 1. So one can understand what we are doing. In fact, we have this result when we start with a connected graded coalgebra. This co-ideal IC is the only graded such that the quotient is strictly graded. This means that it is okay connected, and the primitive elements are exactly the first degree part. And there is also when we consider the projection from C to the quotient, we have a bijection between the first degree parts. Moreover, this is also the largest co-ideal of C contained in the sum, on the direct sum of the Cn with n bigger equal than 2, and also the only one such that the primitive elements are coincide with C1. So just a sketch, what we are doing is this. So clearly the grading of the quotient is given by this. Since we are the ICN are the IC is a direct sum for n bigger equal than 2. The grading of the quotient is clearly given by the same 0 degree component of C, which is one-dimensional, because we are considering a connected coalgebra. So this is just one-dimensional with a group like one. Then the same or isomorphic 1 degree part, and then you have this quotient for the degree bigger equals than 2. So clearly 1b, let's say, is satisfied. What is interesting is also 1a, and yeah, to show that the primitive elements of this quotient are exactly the first degree part, and so C1. One proves equivalently that the same ideal I, but associated to the quotient is 0. So you have just to consider the previous map, exactly this, but for the quotient. And what one can show is that these are injective for all n bigger equal than 2, and so the co-ideal I is 0. And why these are injective? Because the delta, this map here associated to C, are just the composition of the one associated to the quotient with the projection over the n component. But now the ICN is exactly the kernel of the delta C, the delta 1n associated to C. So these map are clearly injective for all n bigger equal than 2, and then this ideal 0, and this is equivalent to us that the primitive elements coincide with the first degree part. So what we have is this when we start with a graded connected of algebra in Dieter-Drinfeld module, we can quotient it with this I to the R, and we obtain a graded connected co-algebra such that its primitive elements coincide with the first degree part of it, which coincide also with R1. But now, since this I to the R is the largest co-ideal in this direct sum here, the other two co-ideals, these two guys, where we multiply with R from the left and from the right, must be contained in I to the R. So this is also a two-sided ideal, so a bi-ideal. And then this quotient is a connected bi-algebra and then a Hopf algebra in Dieter-Drinfeld, because as we told also before, we can always build the antipode in this case. So we can give this definition when we start with the Dieter-Drinfeld module. A graded connected Hopf algebra in Dieter-Drinfeld module is a pre-Níchols algebra of V if the first degree part is isomorphic to V in Dieter-Drinfeld module, as Dieter-Drinfeld modules. R is generated as an algebra by the first degree part. And a pre-Níchols is a Níchols also if R is strictly graded. So the primitive elements of R coincide with R1. So we know that in this case, when we start with the graded of algebra, we can obtain this quotient here, which is still a graded of algebra. But if we start with from the tensor algebra, we are able, in fact, to satisfy all the three conditions, and so to obtain a Níchols algebra of V in the sense of this definition, just exactly in this way. So if we consider an arbitrary Dieter-Drinfeld module, in fact, we quotient the tensor algebra with this IV, which is define as before as the largest co-ideal contained in this direct sum. And so it is this direct sum of these kernels of this map. Okay, so this is a Níchols algebra in the sense of the previous definition. And it also has this universal property when you consider a pre-Níchols algebra of V. And so with its ISO, because we recall that pre-Níchols is such that the first degree part is isomorphic to V. Then you can find exactly one morphism from the pre-Níchols algebra to the Níchols algebra, which is a morphism of graded of algebra in Jeter-Brinfeld modules, such that F is exactly the restriction of pi to R1. And this pi is surjective. Moreover, it is bijective if and only if R is a Níchols. And the proof is easy, and it's just use the universal property. So consider F minus 1 from V to R1, and then use this result here of before that I recall briefly is exactly this one. So this universal property, more specific this case here, because this applies also for this morphism, just because the first degree part is containing primitive elements. So we can use this theorem. And we know that there is a unique morphism, F, from the tensor algebra to R, defined by this relation here. And this F is clearly surjective, but it is also bijective when we restrict this F to the degree 0 and 1. So its kernel is contained in the direct sum with n bigger equal than 2, but here the ideal, the bi-ideal IV is maximal, and so the kernel of F has to be contained in it. Then you obtain just a surjective map from the quotient of TV with this kernel, which is isomorphic to R. This is just because F is surjective into the Níchols algebra, and this restricts to and this restricted to R1 is exactly F. So this is the construction of Níchols algebras, and it's their universal properties. Now I would like to give some examples from braided vector spaces. So just a remark: when we have an abelian group and a set, and we consider a vector space with basis xi, then if we choose for all I an element in G and the character chi I, then we can build this graded vector space, which is just the direct sum of the vector space generated by the xi. And this is a Jeter-Brinfeld module, just define the action in this way here. So using the characters of the group. Now, if you choose, if you define C as the braiding with component BV, you obtain exactly a braided vector space of diagonal type. So your C is such that evaluated on xi tensor xj is just the flip with some scalars qij, which are exactly the bi-character xj evaluated on gi. And vice versa, if you start with a braided vector space of diagonal type, you can define the abelian group with basis gi and character ki defined in this way, so that the V becomes a Jeter-Brinfeld module in this way. And again, C dV is C. So this is just to say that Jeter-Brinfeld modules over abelian groups are essentially braided vector space of diagonal type. So we want to give some example of Níchols algebras coming from braided vector space. So the easiest one is just consider V with the identity. What you obtain is that the Níchols algebra is just all the tensor algebra if the characteristic of the field is 0, while you have to quotient with tensorans bigger than P if the characteristic is P. But now we can give some more sophisticated example. So first, an easiest one. So start with the braided vector space where V is one-dimensional with basis X. So the braiding has to be defined in this way here. So where Q is just a not zero scalar. Then what you do is define this NQ in this way. So if Q is different from 1 and the order of Q is finite, put the order of Q. If Q is 1 and the characteristic of P is the characteristic of the field is P, then put P, and otherwise you put infinity. Then what you have is that, of course, the tensor algebra is the polynomial algebra generated by X, because V is one-dimensional, and your Níchols algebra is just this polynomial algebra quotient with the ideal generated by X to the NQ, if NQ is finite, otherwise it's all the polynomial algebra. Now we can also generalize this example to braided vector space of diagonal type, let's say, for what we consider just a vector space with basis xi and braiding of diagonal type, in fact, where these qij are different from 0 and are such that this relation is satisfied. So qij, qji is 1 for all I different from j. Then define ni as and qii as before. And what you obtain is that the Níchols algebra is the quotient of the tensor algebra by this relation. So first, you consider this relation here. So xj minus qij xj xi for I less than j. And then you also quotient with these powers here. So xk to nk if nk is finite. Now, from this, we can obtain two well-known examples. If we assume that our qij are 1, so our braiding is the canonical flip, and then we obtain what? So if our qij are all 1, we can see that from this relation here, we obtain, exactly the symmetric algebra. But now we are exactly, I come back here, in this setting here where Q is 1, because our Qij are all 1. So we just also have to quotient with some powers of X if we are in characteristic P. Otherwise, we are finished. So we obtain, in fact, the symmetric algebra if we are in characteristic 0, or otherwise we have to quotient the symmetric algebra with these tensorants bigger equal than P, of degree bigger equal than P. Another famous example is if we consider Qij equals to -1 for all I and j, so the braiding is minus the flip map. What we obtain from the previous example, here we just have a relation which are xi, xj plus xj and xi. And we are in this setting here because Q is -1, so it's different from 1 and has finite order. So you also have to quotient with the square of the xi. And what you obtain is exactly the exterior algebra. So when you choose your qij all equal to 1, so as C you choose the canonical flip, you recover the symmetric algebra or a quotient of it. While if you assume that your C is just minus the flip map, you recover the exterior algebra. I would like to finish just with an application to pointed of algebras. So consider just a pointed of algebra H, or more in general, a of algebra whose coradical is a of subalgebra. We know that the coradical is a subcoalgebra, but it is not always a subalgebra. If this happens, then the graded algebra associated to the coalgebra filtration is a of algebra, and we have this theorem here. So consider H as before. So a pointed or of algebra whose coradical is of subalgebra. And consider the projection from the graded algebra associated to H to the coradical, which is just the group-like, the group algebra of group-like elements, if we consider pointed of algebra, and E is the inclusion. Then one can define the R as the coinvariant elements. And this is a of algebra in the category of Dieter-Drinfeld modules over the coradical. And there is the well-known bosonization isomorphism from the group algebra, the graded of algebra associated to H, and the bosonization from, of the coradical with this R. But now, if one considers the subspace of primitive elements, this is still a Dieter-Drinfeld submodules. And the subalgebra generated by it is isomorphic to the Níchols algebra of these primitive elements. And so what one obtains is exactly that the gradient of algebra is isomorphic to the bosonization of R with the coradical and contains as a op subalgebra the bosonization of the Níchols algebra of the primitive elements with the coradical. So one can see that Níchols algebra appear naturally in this context, and classify Níchols algebra is important to classify this H such that the coradical is a op subalgebra. So more specifically, if we consider pointed off algebra, this is just a group algebra. The coradical is just a group algebra, and so classifying Níchols algebras over groups is important to classify pointed off algebra. As for sure about this we'll speak in the next talk, Benjamin, so about classification of Níchols over groups. And with this I finished, and I thank you for your attention.
Hey, thank you for the nice talk. Are there questions? I think Bishan had a question, right?
Yeah, I don't actually know what a pointed hop algebra is. If you could explain.
Sorry, I don't.
What is a pointed hop algebra?
The pointed hop algebra is when the coradical is just given by the group algebra generated by group-like elements.
Okay, thank you.
More questions? Maybe one thing I can ask. So you were saying that if you found a bi-algebra, then it was kind of automatic that you got the antipode. Can you explain us a little bit how you get the antipode out of nothing somehow?
Yeah, in fact, what you are able to do is this. So when you have a bi-algebra, sorry, what is the result? Okay, when you have a bi-algebra, okay, here is just a bi-algebra in Yetter-Drinfeld module, but the fact is that this is a graded bi-algebra in Yetter-Drinfeld module. This is automatically an op-algebra because you are able to build the S in this way. So it is just these sums here where the power of n refers clearly to the convolution product. You can verify that this is an antipode.
Okay, very nice trick. Okay, cool. And maybe a second question. So all of this is kind of based on the braided monoidal category of Yetter-Drinfeld modules, which is equivalent to the category of tetra modules, right? So there you have the tensor product over H rather than K.
Yeah.
So like, is there a way to understand these Níchols algebras in the category of tetra modules rather than Yetter-Drinfeld modules, or is it not interesting?
This I don't know. No, I think it could be interesting, but I don't know about this. I always see Níchols algebra related to Yetter-Drinfeld, the category of Yetter-Drinfeld modules over op algebra, or more specifically over just the group algebra, because when you have pointed op algebra, you have just Yetter-Drinfeld modules over group algebras. But I never seen this the interpretation of Níchols for tetra modules. But you are right. Yeah, the Yetter-Drinfeld modules are tetra modules when you have an op algebra. So you should have an interpretation. I don't know if this could be interesting and if it's done, but yeah, I don't know. Sorry, can you hear me?
What?
Sorry, can you hear me?
Yeah, I'm probably having some problems with mic. Can you hear there?
No, I cannot hear you.
If you hear me now?
Yeah.
Now you can hear? So I would ask you to.
Hi, Andrea. It's Andrea. My question is if you know if there is some nice property on the category of Níchols algebras, like it is monoidal, it is braided, it is infinitesimally braided.
Okay, so Níchols algebra are just of algebras are just braided of algebra with some properties, as you can see here. Níchols algebras are just okay. Here is the definition of Níchols algebra are just connected of algebra in the differential module, so they form a subcategory of algebra in the category of differential module. So I think that they should be monoidal. I think because for sure every op monoid in a braided monoidal category is monoidal. In this case, we are also considering H with bijective antipodes. So for sure the category of algebras in the category of differential modules is monoidal. I think also that this subcategory of Níchols algebra should be. I don't know for surely if they are. I know that there are some problems with braidings, in the sense that I'm not sure, but I think that it's not so easy to define a proper braiding on the whole category. But I'm not sure for this, and for sure I don't know if they are infinitesimal braided or or something more stronger. Yeah. But they should be for sure monoidal. I think that there could be some problems with braiding, or I'm not sure if you are able to define a braiding for the whole category. But I'm not sure about this.
Okay, thank you. So if there are no more questions, let us thank the speaker again. And now there's a 10 minutes break.